Good afternoon. I'm Jim Kitchen, work at Anaconda. This is Erik Welch. He works at NVIDIA. And we're going to talk about GraphBLAS for sparse data and graphs. A little outline. We're going to first talk about graphs and their equivalency with sparse arrays. Go through 3 algorithms: Pagerank, single source shortest path, and breadth first search. Then we'll talk about the BLAS and where GraphBLAS got its name. And then talk about python-graphblas tech stack. And then NetworkX, some dispatching to GraphBLAS algorithms and collaboration work that's going on there. All right, so this is a graph. If you're expecting a bar chart, you're in the wrong place. This is about networks and graphs. Hopefully you've seen a graph before. But as we look at sparse arrays, we start with a sparse vector. So there's one value for every node, because almost every algorithm is computing something about the nodes. So we need a place to store that. And then we have an adjacency matrix. So 7 rows, 7 columns, it's square, with a value that represents each edge. In this case, it's an unweighted graph, so they're all 1. One note, if the graph were undirected, then this would be symmetric. In this case, it's a directed graph, so it's not symmetric. With the adjacency matrix, if you look along one row, in this case, we're starting with node 7, and rows represent outgoing edges. So you see in the graph at the left, 7 points to 3, 4, and 5. We've got a 1 in columns 3, 4, and 5. If you look down columns, then it represents incoming edges. So in this case, there's only one incoming edge at 2, and so in row 2 of column 7, we've got a 1 there. That's how they work. If this were weighted, then instead of 1s, you actually have numbers there. So that same edge from 2 to 7 now has a 4.1. Otherwise, it's the same. All right, put your math hats on. We're going to get into some algorithms. We're going to start with Pagerank. This is super simplified, so we are ignoring personalization. We're ignoring dangling nodes. We're, in fact, ignoring damping, just the core of what Pagerank is. So first we have our nodes. We're going to initialize them all with 1/7 because we have 7 nodes. They're supposed to add up to 1. Next, we need to take our adjacency matrix, and we actually normalize each row so that each row adds up to 1. The reason being that in Pagerank, one node represents a website, and if it has 2 links, then you give its value cut in half so that a page that has 10,000 links doesn't get overpowered. You divide it. With that, then we start doing vector matrix multiplication. Here, if we're just looking at node 5, it becomes a dot product of our current node values, column 5. It's sparse, so they're not all going to be there, but if you see, it's a representation of all the incoming edges, because we're going down a column, of all the incoming edges and the weights that come down into node 5, and that's the new computed value. We, of course, do the full vector matrix multiplication, get all the values. We keep iterating until it converges, and that's Pagerank. That's all it is. If we look at some code, NetworkX actually has multiple implementations of Pagerank. So on the top, here's the linear algebra version. That they have one for NumPy and SciPy sparse. We're going to go over some number of iterations. We keep a copy of X so that we can compare if it's converged. But here, we're just doing X times A. That's the vector matrix dot product. In this case, we have the damping and the 1 minus damping thing. We'll ignore that for now. But that's it. That's it. And then you check, are you converged? And if so, you're done. In the pure Python version, like not using linear algebra, that dot product becomes a doubly nested for loop. Obviously, it's going to be slower, but in the end, it's doing the exact same thing. So if we were to look at how is the performance in these, I hope you can guess that a doubly nested for loop in Python is not the way to go. Sure enough, NetworkX doesn't perform as well as SciPy sparse. An interesting thing happens with NumPy, though. It's still using the same linear algebra approach. And I should just say, this is not real data. This is more like implied generalizations about what happens. But at some point, your graph gets large enough with NumPy because it's dense, not using sparse. And we're talking a billion by a billion. Most of the computation is just computing 0 times this, 0 times that. And it actually gets worse than NetworkX. NetworkX at least only deals with the actual edges. So this shows some things, specifically sparse linear algebra. And that sparse is key when you're doing graph problems. You get the benefits of all that, but it's got to be sparse. All right, so do we get to celebrate? Yes, in this case. Are all of our graph problems solved? Would I be putting it up here if it were? No, of course not. Pagerank, unfortunately, is a bit of a special case. But we're going to talk about how we can maybe solve that problem. So first, let's look at single source shortest path. If you aren't familiar, you start with one node, and then we're trying to get to every other node and see which is the shortest path. So there's several paths you could get from 1 to 6. You could go along here. You could go through 7. But the shortest path is through 4, 3, and 6. And how do we compute that for every node? So this looks just like PageRank. We're going to start, initialize our node. In this case, I've got node 1. I'm going to put a path length of 0 because it has a path length of 0. Next, we need to extend that path length where we take the current path length and add the different values. So I know that from 1 to 2 better be 2.2, and to 4 it needs to be 1.9. And I am asserting that we can do some vector matrix-y thing to get that answer. The question is, what goes in this box here? Normally we would do the sum of k, sum over k of ak plus or times bkj. In this case, that would just give us zeros. It's not what we're looking for. Instead, we want something like this. I want the min over k of ak plus bkj, right? I want to take the current value and I want to add the path length. And then if there were multiple path lengths to get there, instead of adding them at the end, I wanted to take the minimum, right? I'm trying to find the shortest path. So these are called semirings. What we normally think of, you all learned in math class, all those libraries have is the plus time semiring, because you're summing, so that's a plus, and then you're multiplying, that's times, so it's plus times, we read left to right. That's just the name they gave it. We instead want to use the min plus semiring for this vector matrix multiply. That seems a little weird. Most libraries can't do this. GraphBLAS does. It introduces this, and it will give us this exact frontier that we can then feed back in and keep iterating. So now we've got this frontier. We do a min plus operation on that. We get the next value. And as we feed it back, notice there's actually another value here on 1, 3.8. It's because from 1 we went to 4 and back. And so we have 3.8. We don't want to just replace that. As we put the frontier back to the previous, we will actually want to do a minimum operation. So it's element-wise between these two, again, taking just the minimum. That is called accumulation in GraphBLAS, where you take that and we feed it back in via a binary operator. In this case, what we do is we actually treat missing values as plus infinity, so that a new value will always just replace it. And that's how it still works. Let's just zip through the rest of this. This is the code for python-graphblas to do single source shortest path. 5 lines. So you got while true, I take my frontier, I duplicate it, so we have a copy. I then take the frontier and I'm doing matrix multiply with A using the min plus semiring. I then update the frontier using the minimum operator. So even though in this demonstration I was showing we had this next frontier so we can mentally think about it, in GraphBLAS you actually take a vector times a matrix and update the vector all in one operation. It can do that. Very powerful, very efficient. And then we just check, is the frontier equal to its previous, and break. So that's 5 lines, single source shortest path. Very readable. Let's move on to breadth first search. Get a little bit more complicated here. So we have one node, and again, we're just trying to step out. So the second level, you can get to 2 and 4. From there, you can get to 3, 5, and 7. And last, you get to 6. You can also compute parents, where if I look at node 7, I say, how did I get back to the start? 7 points, its parent is 2. From 2, I get back to 1. From 1, I'm at the start. So we can compute levels and parents. So let's do the same thing. All right, so I'm going to initialize frontier, level, and parents. So this time I got 3 of them. It's getting more complicated, but it's okay. So the level, I'll put, where this is the first level here. The parent, we're starting with a 0, and the frontier, I'm just initializing it with a 1. So the steps we go through here is I'm going to compute a new frontier where the parents are missing. All right, this where the parents are missing doesn't make much difference now, but you'll see it's key. I basically take the shape of the parents, and because there's already a value here, I put an X and say you can't compute a value there. All right, then I take this new frontier, and I'm, again, using the structure of this, and I'm going to update the levels so that the 2 structures, I'm just updating positions 2 and 4, but instead of using the values, I put the level in those 2 slots, okay? The parents, I actually do pull over the actual values, but again, I'm ignoring the 0 here. I'm only updating where the structure was here. And lastly, I update the frontier, again, just these positions, but now I'm actually taking the index here. So I know I need to fill this in with the index, so it's going to read 2, 2, 4, 4. Seems a little weird, just run with me. Let's repeat. Okay, we're now moving on to the next frontier. So I have a 2-4. I'm using the min times semi-ring to do this computation. And now again, I say I want to compute the new frontier where the parents are missing. My parents just got more filled out. I've got 3 entries, so I can put an X there and say, don't compute that. So here I'm think about this. I'm doing a vector matrix multiply, but I'm specifically telling my compute engine, you could ignore these 3 columns. Don't compute them. So instead of needing to do 7 dot products, I only need to do 5. This is called masking. And it lets your vector matrix multiply be a whole lot more efficient as the algorithm progresses and you start filling in things. It's almost as if you look at my graph here, like these lines just sort of win away for that computation. So I'm going to take these and just repeat the same thing. So I've got 3, 5, and 7. I fill those in with 3s because we're on level 3. I take the 4, 2, 2 and actually put them in my parents. I go up, pop these up, put the index positions in, move on. I've got 1 more to do. I fill in position 6. And at the end, I go to compute the new frontier. It's empty, so I'm done. And here I've computed my levels. 6 is in level 4, 5, 3, 5, and 7 are on that, and the parents are all computed. So it was just a series of vector matrix multiplies with a couple of weird things, but here is the Python code. 7 lines this time. So I'm going to walk through, I need that I to keep incrementing, so I've got a for loop that will go at most n nodes. I take my frontier times a using the min times semi-ring. I'm going to update my frontier using the complement of the structure of the parents. So that's where I said where the parent wasn't filled in. That's saying take the structure of the parents, complement it, invert it. And then if there was anything there, just wipe it out. That's what the replace is. If the frontier at that point is empty, then you're done. Otherwise, I take my frontier shape and use that to mask the levels, and I fill in I. I take the frontier shape, take the frontier itself, update the parents, and then I finally update the frontier by replacing it with its own index. So a series of couple operations, and you do breadth first search. Now that we've got those, let's jump back and talk about the BLAS. I hope you guys have all heard of BLAS, the basic linear algebra subprograms. This was done back in like the 80s and 90s. Someone realized there's these very common, mathy operations, linear algebra stuff, vector, vector, matrix vector, whatever. If we can just write a defined API, then we can have a nice separation of concerns. The hardware people get to go optimize this to their GPU, their specialized CPU, whatever else they do, make it super fast. And the developers just get a link against those libraries and get all the speed benefits. So it's really elegant. And so there were some academics a couple years ago who said, we need the same thing for graphs with this sparse linear, so we're going to call it GraphBLAS, inspired by that. So they have a very simple sparse linear algebra API. It does things like matrix multiplication, element-wise operations. You can do reduction, matrix down to vector, down to scalar. You can select things, find all the edges that are larger than 5 or whatever. You can assign, extract, but it's well-defined and simple so that you can, again, have that same separation of concerns. But it's not just normal sparse linear. There's these 3 key features. It has semi-rings for the normal matrix multiply to expand what that means. It does accumulation and this masking that I talked about. And that really is the core essence of what makes GraphBLAS amazing. So with that, I'm going to turn it over to Erik, who's going to talk about some more things.
Thank you, Jim. That was great. Now that you've beaten down their minds, I can tell you what to think about all this stuff. Okay. So I'm going to talk about the key takeaways. Going to impart is that GraphBLAS is fast, and it's fast for a lot of the reasons that Jim talked about, of the masking and the avoiding the work and allowing the backends to actually do the magic that they can do, because we're expressing this at a high level. And just by expressing things in linear algebra, we're naturally exposing parallelism, and hardware is great to use that. It's also very scalable, at least in principle, because we as a community know how to make arrays, matrices, distribute them on multiple machines, and perform matrix multiply and lots of operations. And indeed, we have a prototype of Daskifying, using Dask to run GraphBLAS in a distributed environment. This is very experimental, so it's not ready for prime time yet, the distributed thing. So if you want like truly scalable, fast graph algorithms, cuGraph is the best library in town, and I work at NVIDIA. I work on the cuGraph team. Have your organizations buy lots of GPUs. Thank you. Back to GraphBLAS. It is also very flexible for many of the reasons Jim was saying. It's flexible for more reasons than just what he was saying as well. And it ties into the fourth point of it's designed for longevity. Talk with me in the hallway or ask questions later to expand upon this point. I'll just say that this allows implementations to innovate now and in the future. There are sparse accelerations, hardware being worked on, like there are sparse tensor compilers. It's an active area of research. So this is not a solved problem, and there will be innovations. But if they target the GraphBLAS API, now all of a sudden, like, it's easy for everybody to use and take advantage of it. But so what? And who cares? Like, who uses graphs and sparse data? This is kind of a hard question to answer cleanly because graphs are kind of used everywhere. Lots of data naturally wants to be sparse. Like we can have a 2 to the 60 by 2 to the 60 array, a matrix, with just very few things in there. So you can actually that's almost enough to show IP4 internet domains. So it's used everywhere, but it's kind of a niche application where it's used. But because GraphBLAS is fast, it does open up a bunch of opportunities. So next, I'm going to talk about the big picture of like what is python-graphblas and where does it fit in. And we often view this as like the technology stack or software stack, but I'm just calling it the stack because we're starting with the math specification. This has been known a while that we can express graph algorithms in terms of math, and it often shows up as pseudocode that looks kind of like this, where we have like the semi-ring in the middle between the two operands, and if there's a accumulation. But if I'm reading papers, I'd rather read pseudocode like this than pseudocode that does like nested for loops. Thank you very much. On top of the math is we actually need to reify this into a specific C API. And the C API tends to be very verbose, and it's kind of hard to read if you don't know what all these fields mean. And even if you do, it's a lot to take in. Because there's a whole lot that goes into a single call, because you need to have the outputs, the accumulator, the mask, the semi-ring, the inputs, and whatever this descriptor thing is at the end. And take care, I am calling this the C specification, not the C implementation. So GraphBLAS is a specification, not an implementation. This is very kind of, like pragmatically, there's not much difference, but it's actually matters a lot in principle because there could be lots of implementations. And we allow these implementations to innovate. So to allow them maximum flexibility to innovate, the objects are opaque. Which means that like we don't say what the data structures ought to be to represent a matrix. You could use any kind of format you want or data structures to represent the matrix and the operations. On top of this is like the actual C implementation, which is Sweet Sparse GraphBLAS by Tim Davis. It is a great library, makes it very easy to use. It is very fast on many of benchmarks. Uses OpenMP for single machine parallelism on the CPU. GPU support's coming later. MATLAB uses this library under the hood, so it's used widely and reliable. And there's a lot to say about Sweet Sparse GraphBLAS because it really makes things nice to use. That it automatically chooses what data structures to use, and if you're like mixing and matching, it'll actually make them pretty fast. It has all those mixed kernels. And it lets you like specify, I want it like this format, or I'm going to bring data in this way or that way. It has a JIT, so you can have like user-defined functions, user-defined types, where you can just use a Python functions and use numba, or you could give it the C string to compile. Yeah, and GPU support is coming soon. On top of this is our library, python-graphblas. where we have to use the C API, but we want to make it look more like the math specification. But we also need to adhere to, it needs to be valid Python code. And so we have the syntax showed here, kind of like shows how we do the accumulation and then choosing the simmering. And that line there corresponds to a single call in C. And I think this is the most natural way to like read and write and think about a GraphBLAS. You can install it from pip or Conoforge on all major platforms and architectures. Go check out the docs. We do aim to support any implementation. So if more come out, we want to support you. We want to be vendor agnostic. On top of this is where we collect all the algorithms in GraphBLAS algorithms. We're not very creative with our naming. We currently have more than 80 NetworkX algorithms. This may sound a lot. NetworkX is a huge API, so there's a good chance it does not yet have like that one algorithm that you need. So please let us know what you need. But this, yeah, it looks like NetworkX because we are targeting NetworkX as an API so we can be a backend to NetworkX. In NetworkX 3.0 and 3.1, we've added dispatching. So you can pass it a GraphBLAS matrix directly to NetworkX, and it'll run our algorithm. And we test using the NetworkX tests. So it's trustworthy in that sense. And so our vision, like we still have a lot to make this nice and usable for everybody to take advantage of it, but our vision is to accelerate libraries that use NetworkX. The other view of like, this was the tech stack. I like the tech volcano, the software volcano, where as you go up, things get more specialized, things get easier to use. And at the top of this is NetworkX and lots of libraries, lots of applications use NetworkX. And you see some of the fields in which this is used. Don't have time to talk about the maps, social networks, biology, genomics, power grids, and so on. Disease propagation with that. So let me do a quick demo of, okay. Some benchmark, well, to show what our library looks like, the data structures. That's a matrix. That's the one that Jim had in his demo. So this is our say matrix. So we're going to do a benchmark on a graph with 40,000 edges, which is not very big, actually. So our matrix actually has 80,000 entries because it's symmetric. So with GraphBLAS, that was that fast, and with NetworkX, it is, we're still waiting. So we're doing square clustering. I think it's very interesting that we can actually count the number of squares with linear algebra. So yeah, and these match. It was a lot faster the second time for some reason. I will prime the questions. So taking a peek at our supplementary material. Oh, we're no longer in presenter mode. Jim, help. Okay. Because we're pretty much out of time. So if you want to ask questions about comparison with SciPy-sparse, like why do we need another sparse library? For all the reasons Jim talked about. Simmerings. And it's single threaded, and it's not expressive enough. Like missing data does not mean zero. It means missing in GraphBLAS. So we could talk about this, and we could dive into the anatomy of a call, or what is a simmering. Yeah.
Okay, thank you.
Thank you. Please raise your hand if you have any questions.
And otherwise, if you're a hybrid participant, please post your questions online. We'll be watching that too.
Hi, thank you for your talk. I was wondering if there's any specific data types that you think it's better suited or has better performance, or probably there's no difference.
I mean, so the GraphBLAS supports, integers, floating point, unsigned integers, Boolean, but it does support user-defined types. So you could build structures and work with those. that's kind of what it does. If you're using strings, probably not. Got to draw the line somewhere.
So I just wanted to say, as I guess the core NetworkX team, this is really cool, and we're really excited, and hope people try it out. NetworkX Dispatch. This is we'd love to have some feedback. We're working together with the team, and this is NetworkX is widely used. People love the API. They love looking at the code, but it's slow, and this is like the best of both worlds. We, as an open source community project, don't have to support having a really complicated project. We can stay in pure Python. It has a pedagogical value that you can still look at the code. The API is beautiful. And now we get this extreme speed up, which is just amazing. So thanks a lot for the work.
Thank you. It's been fun working with you. And just in case you didn't see on this, we're calling NetworkX's square clustering, passing our matrix, and NetworkX dispatches to our implementation. So that's the magic right there. So it is working live today.
Thank you, gentlemen. What is a semi-ring?
All right.
Cats.
Cats.
This is it, cats. Yes, this is more fun. All right, so just to, it's basically a monoid and a binary function together. So normally this is where you take all your dot products, you're going to multiply them together, and then reduce to a single value by adding them. The thing is, your binary function does not have to be the same domain. So this is where you're taking money and a pet store and a cat comes out. So a valid, it's weird, but once with monoids, it's got to be cat, gives you a cat. But so you could do something like the all greater than semi-ring, where I literally take these values and say, is this greater than this? And it gives you Booleans, and then at the end I reduce them all using all. That's a valid semi-ring. It feels really weird to think that you could do matrix multiplication that way, but mathematically it's sound. And so that's why these math properties, but that is essentially, a semi-ring is something that's valid to do this matrix multiply-ish thing.
We do have a question submitted on Slack from Paul Ivanov, who is here. I'm supposed to credit the speaker. Yeah, the question. Anyway, Paul asks, can you comment on current float stability situation when using GPUs compared to using CPUs?
The GPU support is not there yet, so I cannot comment. Rick Ratzel with cuGraph may be able to comment on this. He can't comment either.
Okay, yeah, can you repeat it so the remote people can hear? Because I probably couldn't hear you, sorry.
Yeah, so Rick can't comment on that either, but I'm curious why you ask.
Paul likes to throw random questions, yes. No, it's part of a stimulating conversation, yeah. Effervescence, right? Yeah.
Okay, I know Paul's very shy, so that's why he posts questions on Slack. But if anybody here has any more questions, I actually have a question. So one thing you mentioned in your abstract is that adoption of graph and sparse data techniques is slow because there's maybe not that much known about it. And I was wondering, so I'm in a physics lab, so most of my colleagues are physicists. They know Python, they know how to code, but they're not computer scientists. And a lot of them, if you ask them, what is a graph, they will say a bar chart. So what have you found? We use graphs in our internal software, and actually the tool we use that is based on graphs is extremely stable, extremely fast, but there's like probably 1 or 2 people in our team who knows how to maintain it because they're, the knowledge of graphs in our team is not as wide. So I was wondering, do you have any experience like teaching people graph theory who haven't done computer science majors?
Not really as far as teaching, but yes, this project, python-graphblas is 4 years old at least. So this is why we want to give talks. It's also why the marriage with NetworkX is really good. They need speed and we need adoption. And people who come to Python knowing they have a graph problem tend to reach for NetworkX first. So instead of trying to fight them to do SEO ranking to get up in the knowledge share, we'll just start with NetworkX and keep using NetworkX, but under the hood you're using this. And again, not everyone needs to know sparse linear algebra to benefit from it. But we do need some people who are excited about to start writing more algorithms for us. So yes, if that's your interest, please come talk to us. We would love to have lots of collaboration.
We also use cats and superheroes a lot.
Are you going to be at the sprints this weekend?
I will at least be here Saturday, probably with the NetworkX people.
Awesome.
Awesome. Well, I think that's our last
We're at
question. So we can end for now. We're going to meet back downstairs in Zlotnick for the lightning talks. I hope to see you all there. Definitely important. Like, you don't want to miss out. So, but let's thank our speakers once more.